Okay, part two. I gotta do one more of these, and then I'm getting hungry. Okay, this was Unit 5, Lesson 2, in which we talked about latent heat, sensible heat, then the big boy, specific heat capacity, aka Mr. C over here, and then I'm going to tell you the two equations for these and some practice calculations so that we can go through them and that you're ready as Freddy. Okay, let's start at the start. Latent heat. Latent heat and sensible heat. These are two terms. And I scrolled to the right page now. These are two terms that describe two different forms of heat, as you can imagine. One of which is latent and one of which is sensible. Let's start with sensible since that is the easiest one. These names are based on real words that should have a meaning to you. Sensible, it comes from the word sense, that your senses can pick up on it. So, sensible heat means heat, energy, that we can feel the difference of. So, sensible heat change means that if we increase the amount of heat energy, there is also an increase in temperature. So, for example, an example of sensible heat change would be I have my little pot of water that I just filled out of the tap. Bada bing, bada bang. I put that beautiful pot on my stove and it starts heating up. And you know what? This was 21 degrees out of my tap, and then I put it on the fire, and right now it's been on there for a couple minutes. It is now 60 degrees. If I take my fat finger and I put it in here, what am I going to feel? About 21 degrees. I take that same finger and I now put it into a 60 degree water. I'm going to feel that heat, the difference in the heat between 21 and 60 degrees Celsius, and that is what we call sensible heat change. Change, heat that causes a change in temperature that we can feel. That's why it's called sensible, because it is from the sense touch, that we can touch something and we can say, oh, there was sensible heat change here because my finger is now on fire and it's very warm. Latent heat, on the other hand, is the exact opposite. And latent comes from Greek, latere, something like that. Latere, I don't know how to say it and I don't know how to spell it, but I do know what it means, and it means to be hidden. So hidden heat. And why do we call it hidden heat? I hope we can kind of see it coming here, that sensible heat is when heat increases and temperature increases, we can sense that difference. Whilst if we increase the heat, latent heat, there is no difference in temperature. It is a hidden increase in heat because the temperature stays the same, but the amount of energy is increasing, the heat is increasing. And how can we think of this? Is if we have our little pot of water now, it's been boiling for a couple minutes. It's been on for a couple minutes and it has reached boiling point. Great. It has reached boiling point. And we keep that fire on. So what is going to happen? We keep that fire on and eventually what we should see is it starts boiling. It starts bubbling, hubble, bubble, boil, and trouble. And then we get gas, creation of gas. And surprise, surprise, this gas is also 100 degrees. But this gas has more energy in it, right? Because this fire has been kept on. This gas has more energy than our boiling water, even though it has the same temperature. And if we recall why that is, it is because that is over here, right? We have our boiling water pot over here at 100 degrees, which has, let's say, 100 joules of energy. If we keep the fire on, this amount of energy is increasing, let's say 200. And here we have gas that is now also at 100 degrees. But wait a minute, it has more energy in it. And that is what we mean with latent heat. That if I touch this boiling water, that's going to feel as 100 degrees. And if I touch that steam, that's going to feel as 100 degrees. So it's a hidden amount of heat that's been increased. Yeah? So phase transitions are latent heat differences. Okay? So if we take this beautiful information and we put it into our heating curve, so here at 0 degrees we have an important part, and at 100 degrees for water, this is our temperature, and this again is our heat. We have it increases and then it plateaus, and then it increases, plateaus, increase. And if you remember, these plateaus are because, yes sir, bonds are being broken. We are breaking down bonds. So if we take the definition of sensible heat is when heat goes up as well as temperature going up. We can see that this is the case for these slanted parts. Oh my god, I'm so popular. It's for these slanted parts. Temperature is going up as well as the heat is going up. So these parts here, I really wish I could use some color right now. Does this work? These parts right here, these slanted parts, are examples of sensible heat. Why? Because as we increase Q, so does our temperature. I can feel the difference between me putting a finger here in the water at 20 degrees versus at 100 degrees. I can feel it. Sensible heat change. Okay? Then, these parts here, I hope we guessed it, is what we call our latent heat. Right? Because, yes, we are increasing the amount of heat. The fire's been on. There's more energy in these. There's more energy within these, the water or ice wherever we are. But we don't see a difference in temperature. What do we see? We see that ice is melting, and we see that our water is boiling or evaporating. Yes? That is our latent heat, and this will be our sensible heat. Coolio. In this same vein, we can take our information here and say, okay, our boiling water at a beautiful 100 degrees, and this steam that has come off of our water also at 100 degrees. Which one of these has more heat energy? Yes, sir. That is our gas. Right? The heat's been on and gas has been formed. The same temperature, but more energy within this gas. Okay? So a question could arise in which it asks, hey, and I've said this example before, I have broccoli right here. Would it boil faster if I put it inside this boiling water, or if I put it inside of a steamer where we are boiling, in a sense, with steam? We're heating up our food with steam. Then what should come to your mind is, okay, if I put it in the water, yes, it's 100 degrees. However, it has a lower amount of heat energy in comparison to this gas. It has more heat energy than this water. So our steamer, if we have steam at 100 degrees, will more quickly boil our broccoli. Yes, that is one way to explain this. There is more heat in here. Another way you can go about this is say, well, if we are boiling our water, let's see where we are on the graph. We're here. And so part of the energy of our fire is going into breaking the bonds of water, which is wasted energy in a sense if we want to boil our vegetables. So there's a lot of energy going into our water instead of into our delicious broccoli, at least if you're a big boy or big girl or big they them. Let's be real. Okay, so there's that difference. Here there is energy going into the bond breaking of water, and so not all the energy is going into our broccoli. Whilst if we have our steam, more of that energy is going into the broccoli because there's no energy needed to break the bonds of water anymore. That is latent heat and sensible heat. Beautiful. Should I do the formula now? I think I will do the formula now. The formula for this is very easy. It is Q, heat energy, unit we should know this, is the big boy joule. We times is equal to mass times a constant times the latent heat constant. Okay, and this constant will usually be given to you, and this constant is also different for different things. So for example, I have an example in front of me. The latent heat of melting ice is equal to, I should have had more space already here, 3.33 times 10 to the power of 5 joules per kilogram. And there is our unit. The amount of joules needed to melt 1 kilogram of ice. That is what this means. So yeah, we need, I think, 3.33 times 10 to the power of 5 joules to melt 1 kilogram of ice in this example. So this number will be different for different materials. That is the L, and then our mass is M. And this is in kilograms. Yes? So, an example question could be, we have some gold. We struck it good in the economy. We bought in the dip of the market crash, and I bought some gold. I bought a total of 500 grams of gold, and I searched on the internet, okay, wait, what is the latent heat for my gold? And I found out that that is 63,000 joules per kilogram. And now again, what does that mean? It means that I need a total of 63,000 joules to melt 1 kilogram of gold. And as you can see, that's different to that of ice. Yeah, these are different numbers because they're different materials. There's a different amount of energy needed to melt gold than to melt ice. Now, what is the energy needed to melt half a kilo, right? Because 500 grams is 0.5 kg. Okay, well, let's look at the formula. It's M times L. Our M here is 0.5. And then I times that by our L. And so we have 63,000. And that gives us an answer that is Q is equal to half of 63,000. And now I hope my brain works because I'm getting hungry. Is this? And don't forget the unit because otherwise I will find you. It's 31,500 joules of energy needed to melt my 500 grams of beautiful gold. Too bad I'll never have it. Or maybe, who knows? So this is some calculations that you can do. Another thing, let's say I bought a little pack of ice. There was 200 grams of ice that I bought from the Dirk. I'm not sponsored, by the way. So our mass is 200 grams. I know that my latent heat for melting this is going to be 3.33 times 10 to the power of 5. Let me just write this normal. Is that 3,000? So 1, 2, 3, 4, 0. I think. Correct me if I'm wrong. I'm getting tired. But I think this is 330,000. That's the same as 3.3 times 10 to the power of 5. Okay, so I have 200 grams of my ice. Here it is. This is my ice. It's a big cube of 200 grams. And I want to know how much energy is needed to melt this. Okay, well, I know that here we have my L and here we have my M. What is this? 200 grams is, you guessed it, divided by 1,000 to get to kilograms, 0.200 kilograms. So now I could just plug it into my formula. M times L. I do 0.2 times 330,000, which is equal to 66,000. And you better not forget that beautiful unit of joules. Yeah? That are some calculations with it. So the formula, once again, is Q is M times L. And for the people that love the triangle, bang, 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 Q whoosh, is equal to M times L. So these lines means times, these mean divide by. And how does this work again? Can I, let's see. If I want to calculate a particular thing, how it works is that I cover one with my hand. So I need your hand in this case because I cannot move your hand. Let's say I need to calculate Q. I will cover Q with my hand, and then I can look at the triangle. And I see only M times L. So I know that my formula is Q is equal to M times L. Because when I cover Q, that is what I see. If I need to calculate M, I cover M in the triangle. And what I should see, I'm doing it in real life right now, is, oh, sorry, this is, wait, unprofessional, is M is equal to, and what should I see in my triangle? Q over L. And the same could be done for L, and then we see that is Q divided by M. So sometimes you will be asked to calculate M or L instead of the Q. And this is how you do it. The triangle of destiny is what they call it in the scientific world. Okay, that is that. Then specific heat capacity, it looks difficult, but I will get to it, okay? So, how I introduce this is saying, what would take more energy to heat to 100 degrees Celsius? Is that going to be A, water, 1 liter of water, or is that going to be B, 1 kilogram of iron? And the answer for this is water. Okay, and sometimes this can be a bit counterintuitive. So it takes me more energy to warm up water to 100 degrees than it does to warm up 1 kilogram of iron to 100 degrees. And what is this do? So this, we will come back to this if you're like, what? What does this do because of? It is because of a property of each and every material called the specific heat capacity, aka C. And what this means is how much energy or heat, how much energy in joules is needed to warm something up. And this is a non-scientific definition. The scientific one would be how many, oh my lord, how many joules are needed, beautiful, needed to, sorry, let me think, how many joules are needed to heat up, raise the temperature, raise the temperature of 1 kilogram of our substance by 1 degree. That is what it means. So how much heat do I need to put into something for 1 kilogram of it to be 1 degree hotter? That is what specific heat capacity means. So if I have a very, very, very high C, that means I need to put in a metric ton of energy as fire to heat up my material. And if I have a very, 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 very low C, that means I need to put in just a tiny bit of energy to heat up my materials. And now if we come back to this question, we know that C, well, I know, I'm telling you right now, water has a huge C, a massive C. It has a very high specific heat capacity. Now, what does that mean? It takes a tremendous amount of energy to increase the temperature of water. Whilst 1 kilogram of iron has a little specific heat capacity. What does that mean? Is that it's very easy to warm this up. And you can also visualize this a little bit more by thinking, let's say it's a sunny day out, it's 40 degrees somehow, and I have a cup of water outside, and I have an iron piece of metal outside. So one question you could say is, which one's going to feel way hotter? If it's warm outside, I don't know, maybe you've never been outside, touch grass, but you're outside, it's very warm, and you touch something that's metal, you're, oof, that is warm, that's crazy warm, right? And why is that? It's because metals have a very low specific heat capacity. So at 40 degrees Celsius, they heat up so easily. So a metal gets super warm super easily. Whilst water, in 40 degrees, it's going to take a lot of time for it to get hot. Yeah? That is the specific heat capacity, and that is why it takes more energy to warm up that water than it does to warm up that iron. Another way to think about this is you've probably seen those videos when they have like swords being made and they are glowing hot and they put them in some water. And within seconds, this red glowing hot piece of metal, it turns into just normal metal again, because it is so easy to change the temperature of a metal. Meanwhile, that water temperature from this glowing hot metal doesn't even change a bit. Maybe it increases with 1 degree Celsius. Why? Because it has such a high specific heat capacity. It takes so much heat energy to get this water to warm up. And it takes so little to warm up or cool down iron. And that is where that question comes into. Okay? So, what does specific heat capacity mean? It means how much energy do I need to put in to raise the temperature of my material. And the higher that is, the more energy you need to put in to warm it up. Yeah? This is also why we use water so much, because it is difficult. So for example, when you're showering, you probably put on 38 degrees. Once that hits your body, it will stay warm throughout all parts of your body and all the way to the drain, because it has a high specific heat capacity. It is difficult to change the temperature of water. So we love that. Okay? It can take a lot of energy. Same with sweat. It's so perfect because on our skin, we have little bulbs of water, and eventually they evaporate. But they take so much heat from our body before they evaporate because of that very high C. So remember that. A high C means it needs a lot of energy to change temperature. Low C, it needs little amount to change energy. That is the definition of it. The calculation, which may be a bit more important, but I feel it's easier once you get the grip of what it actually means, what specific heat capacity is Q is M times C times delta T. And if you remember, delta means difference. So, for example, let's say we have an example here. Here we have a difference in temperature, and our delta temperature is equal to our final temperature, 60 degrees, minus our initial temperature, 21 degrees, so a difference of 39 degrees Celsius. This is our delta T. Okay? So the difference in temperature. And sometimes in questions, you will get told, hey, the water increased with 3 degrees. And sometimes it will say it went from 80 to 100 degrees. So remember that delta means difference in temperature. Okay? So let's go over what each thing is again. Q, again, is the heat energy in joules, is equal to the M, which is, again, in kilograms, the mass. C, the specific heat capacity, which is the amount of energy, joules, needed to heat up 1 kilogram by 1 Celsius. That is what this means. And we can also write this as J times this times this. Okay? This is the same, saying something like this is the same as dividing it by that. Okay? So that's where that comes from. So both of these you can see. But you're not expected to know that out of your head. And then temperature, it can be in Celsius, it can be in Kelvin or Fahrenheit, but we spit on Fahrenheit. So we do either Celsius or Kelvin. It doesn't really matter because we're talking about temperature difference here. Okay, let's see if I have some examples. Of course I do. Okay. Oh, we're getting close. Never mind. We're going down here then. Okay. Let's say you have a question that asks you, how much energy does it take? Oh my God, does it take to, let's say, heat, how many grams? Let's say 700 grams of water from, let's say, 50 degrees till 100 degrees. Okay, coolio. And then you will get given this with the C of water being, so the specific heat capacity of water is 4,186 joules per kilogram per Kelvin. So I should actually update this to Kelvin. That is my bad. But Celsius, low-key same thing, but not really, so don't quote me on that. Okay, cool. First thing that I always do, just if you struggle with formulas, if you struggle with physics, write down the formula for yourself, please. That is always the first step. M times C times delta T. Okay, and then I'm going to inventarize. That is not a word, but I'm going to take inventory of what do I have and what do I need. So I need these 4 symbols to be clear, right? These are the 4 symbols that I have, and one of them is missing. So let's have a look. How much energy does it take to heat? Here we go, 700 grams. That is my mass. So 700 grams. What is that in kg? It's 0.7, right? We divide it by 1,000. Bada bing, bada boom. Then we continue. Water, to increase the water from 50 degrees to 100 degrees. Okay, so my delta T is that 100 minus 50, which is equal to 50 degrees Celsius. Perfect. Okay, let's see. Okay, and here I have my C of water, which is 4,186 joules per kilogram per Kelvin, but I am lazy. So that leaves us with Q to be calculated. All right, and now that I have all my digits, I can plug these into my formula. So let's do that. Q is equal to 0.7 times my C, 4,186, times my temperature difference, 50. Let's do some math. So this is going to be what, like 4,200. So I'm just going to simplify it a little bit. I think this is around 200,000. My math game is not that strong. Something around this digit. You can do this calculation for yourself, right? It'll be something like this times 0.7. So we're going to be talking about maybe 100 and not 60,000. What is it? 140,000 joules. Something like this. Okay, so my calculations are not correct, but you should just put this into your calculator, right? 0.7 times my 4,186 times my 50. And whatever that answer is, that is your Q. And don't forget that big boy unit, Mr. Joules, over here. Let's do one more calculation in which we don't calculate Q, but something else. So remember the triangles. We have Q here up top, bada bing. And then we have M times, bam bam, this is the times, C times delta Mr. T over here. Okay, let's remind ourselves how that works. Get me my sticker, even though that doesn't really work. I need your hand for this again. If I need to calculate something for my triangle, let's say in our question we had to calculate Q, I will cover Q with my hand. That's what I'm doing right now, and then I can see my formula, correct? So I can see that Q, what I have covered, is equal to, and I can see M times C times delta T. Perfect. Now let's do it differently. Let's cover M, because we're going to calculate M after this. I'm covering M with my hand, and then I see, okay, the one I'm covering is M equals. That's what we put on before the equals. And then I see that it's Q divided by C times delta T. Okay, so this triangle is the love of my life. I'll also quickly just do these for you because I'm just that much of a generous person. Delta T is equal to Q divided by M times C. As you can see, Q is always on top, so maybe that helps you. Okay, with these in our knowledge pipe, aka the brain, aka the green noodle. No, it's gray. Anyway, I really need to eat. Let's say we have a question where we need to calculate mass. So let's say I have a specific heat capacity. Let's just do 4,321 joules per kilogram per Kelvin. Then I can really do that. That is my C of an unknown material, let's say. We have a temperature difference that we measured, which was 22 degrees, and the amount of heat energy we put into this reaction was a total of 1,000 4,000 joules. Perfecto. So then again, I just inventarize. I see, okay, this is my formula. What don't I have? I do not have Mr. M over here. So I go back to my little skedaddle over here, cover the M, and I see it's Q divided by C times T. Okay, M is equal to Q divided by C times delta T. And now I just fill these bad boys in. My Q, 1,000 joules. My C is 4,321 times 22. Whatever this would give, what would that around be? So this is 40. Did I do this completely wrong over here? 10? Maybe. Who cares? 10, so we get 43k. I think this is very wrong. No, it's not. It's all right. 43k, let's say this is 90,000. About, again, just do this on your own calculator. I'm just playing around a little bit. It should be something like this. 4,321 times 22 is something around 90,000. If I do 1,000 divided by 90,000, that will be a very low number, and that would be my mass in kilograms. Let's say it's 0.001 kilograms. And then I have my answers. And again, do not forget your units, because I will find you. Don't forget your units. We love units in science. Cool. That is specific heat capacity. Okay? Just to come back to the idea of C, what does it mean to have a big C versus a small c? A big C means it takes a lot of energy to heat up my material. It takes a lot of energy to heat up my material. An example of that is water. A small c means something that is easy to heat up, such as a metal. Okay? A metal little bench. Let's say you have a metal bench in the park in Barcelona and it's 50 degrees outside. You will not sit on that bench bare-legged, because that will hurt. Okay? And that's because the C, specific heat capacity, is so low. Those are the two reasons behind all of this. Okay? These are some calculation examples. I hoped that helped. Where were the goals? So now you know latent versus sensible heat. Latent, based on Latent, we cannot feel the difference. So this is when there's a phase change, when we go from boiling at 100 degrees to steam at 100 degrees. We can't feel that difference, whilst sensible heat we can feel. So for example, if water goes from 20 degrees to 100 degrees, I can feel that temperature change. Specific heat capacity talks about how much joules or energy is needed to raise the temperature of my material. And then here are some calculation examples. Q is M times C times delta T with our beautiful triangle. All right, that was lesson 2. Thank you